So so today is just a basic revision session. uh, all the concepts or the topics that need to be covered for the course was covered last week, so in the previous session. So today is just a revision session. I will just briefly go through the entire course of the entire topics that we discussed in this course, and just as a revision video for anyone who is going to prepare for the exam, so they can go through the video recordings, and this video might help them to recapitulate the topics that were discussed in the class. Okay, so there's not going to be any additional teaching, so you can stay if you just want it as a revision session. That's all. So that will be the agenda. Okay, for today's agenda, and this would be only a 1 hour, say around 50 minutes, like that, that session, not that long. Yeah. Okay, sir, then we can just briefly revise whatever we have discussed in this course. So we start with the basic introduction. So we started with the two approach by which we understand the fundamentals of fluid mechanics. So there was the concept of microscopic approach and the macroscopic approach. So for example, pressure, the parameter or the property of the fluid that was taken to refer these two different types of approaches was pressure. For example, in the case of microscopic approach, as the name suggests, we look into the microscopic behavior of the fluid particles and how the momentum by the fluid particles are considered to be the pressure. So it is the change in momentum of the particles due to the collision with other particles are perceived as pressure. This is the microscopic approach. But in the macroscopic approach, we rather than looking into the behavior of each and every particle, we tend to look into the bulk behavior. That is, we time average the total force over a particular region and divide it by the area. That would give you the total pressure. So macroscopic approach is something that we will hold on to for the rest of the discussion for today's course, today's discussion. Just give me 1 minute. And it is the macroscopic approach that we have discussed throughout the course. So, and the concept of this macroscopic approach introduced us to the concept of continuum. Okay, the continuum approach. For example, fluid mechanics in its very essence is a mathematical course, right? So all the concepts such as pressure, velocities can be essentially considered as mathematical functions. But as we know, and we saw that when we were dealing with the Navier-Stokes equation or the fluid kinematics part, we saw that these properties are operated upon by some different differential operators. And for these differential operators to be operated upon these fluid properties, we need that these functions or these flow properties remain continuous. Okay, and for that we took the aid of this continuum approach. We stated that these flow properties, even if the fluid molecules are considered to be made, or if the bulk of fluid is considered as being made of, say, collection of fluid molecules, then also in a certain length scale or limit we can consider the fluid properties to behave as a continuum. Okay, so when we look into it a bit more deeply, so I think I am missing the graph here. Yeah, this one. Yeah, so this graph basically tells us the significance of the continuum approach. For example, while measuring the density of the fluid, that is the delta m by delta v, where the mass as well as the velocity, the volume of the fluid element here is considered to be small enough. But how small? So for example, if this volume of the fluid element is considered to be very very small, then we will encounter rapid fluctuations in its measurements. Okay. Also, if the volume of this elemental volume that is taken to measure density is considered to be very large, then we will not take into account the density gradients in the flow field. In order to do that, there has to be a particular value of this delta V that will give us good values or good values for the measurement of density, which is shown by this constant region. And we saw that this volume is of the order of the mean free path of the uh, 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 length scale of the fluid. For us, that is, it has to be at least greater than this mean free path of the fluid molecule, so that we can avoid this kind of fluctuations. And of course, this should not be that large, so that we will encounter errors while while measurement of this density or any kind of fluid properties. Okay, so let me go back up. Sorry for scrolling out to and fro. Yeah, and this continuum approach that we discussed now was again quantified using a non-dimensional number, and I think by now you are quite well versed with the non-dimensional numbers such as Reynolds number, in this case here Knudsen number, and then there will be other non-dimensional numbers such as Stokes number or Froude number. So these are the non-dimensional numbers that we deal with while studying fluid mechanics, and this is something that you might have been introduced in the last week of this course when we were discussing our dimensional analysis. So similar to it, Knudsen number is also one of those non-dimensional numbers which is used to quantify the continuum hypothesis. For example, which is basically the ratio of the mean free path of the fluid molecule over the characteristic length scale of the flow. And I think we discussed for ample amount of time what the characteristic length scale of the flow means. Okay, so if Knudsen number is much lesser than 1, it would mean that the fluid system is very densely packed and the continuum hypothesis is valid. But if the Knudsen number is much greater than 1, it would mean that the fluid system is very rarefied. Rarefied means that the fluid molecules are much more far apart to each other, which will result in the characteristic length scale of the flow field to be of the order of the mean free path of the fluid molecules to be greater than the characteristic length scale, which will result in different kind of errors in our measurements. That's why we tend to exclude this scenario while dealing with this basic fluid mechanics course, and we limit our study to this limit where the Knudsen number is much lesser than 1. Okay. Then we discussed about the concept of control system and control volume, and why the control volume approach turned out to be the better choice for understanding this basic fluid mechanics course. It is obviously the control system approach, or we can say the Lagrangian approach that we use to study the fluid mechanics system by following each and every fluid particle, is not at all incorrect. It's absolutely correct, and at times much more accurate than the Eugenian approach. But as we pointed out here, like say for example we are taking 3 particles here in this case, so and fluid mechanics system would comprise of n number of particles, where n will be very large as shown here, like around 1 million. So it turns out to be very impractical to check each and every particle every time to understand about the fluid mechanics, the behavior of this fluid mechanics system. Rather than that, what we do is we look into a particular region in the flow field known as a control volume, which we very thoroughly discussed while we were discussing about the Reynolds transport theorem and using mass and momentum conservation respectively to understand the control volume approach. And we saw that this control volume approach gives us a considerably accurate results with much lesser computational cost. Okay, that's why the control volume approach was devised and is still very highly appreciated in the basic fluid mechanics courses. Okay. And then we look into the concept of traction vector, where traction vector was basically used to define the force that acts on a force acting on a or particular area, And you might ask, then why not define it as pressure? Yeah, but pressure is not the only force that acts on a fluid mechanical system, which we eventually saw that apart from pressure, there are shear stresses where enormous stresses as well that act on the fluid mechanics system. So we need to take into account their contribution as well, which would lead into the deformation of fluid element. So that's why, in order to take into account the take into account all these kind of forces along a particular coordinate direction, we define the concept of traction vector, and this traction vector depends on not only on the force, direction of the force, but also of the orientation of the area. That was one of the key features of traction vector, and we saw how it is related to the shear stress tensor. So by tensor we meant that it has two free indices, and we require two indices. For example, in the case of second order tensor, we need two indices to completely define the property. For example, shear stress in this case, or stress in general, is a second order tensor where we need two independent indices, that is I and j, to define completely. For example, if I varies from 1 to 3, j varies from 1 to 3, then tau ij would be a second order tensor. Given its second order tensor, it will have 9 components, and if tau ij and tau ij is symmetric, that we eventually saw from the conservation of angular momentum, we saw that tau ij is symmetric, so that's why it has 6 independent components. Okay, for example, components such as tau tau xy was equal to tau yx. Similarly, tau xz is equal to tau zx, tau yz is equal to tau zy. Okay. Then we used this particular particular approach to find the relationship between the shear stress tensor and the traction vector. So when we did that, we found that this traction vector can be related to stress tensor by this relation, where the repeating indices showed meant the summation over that particular index, which is also known as the Einstein's index notation. So in general, so if I want to point out the application of traction vector in a much more simpler manner, so I would just like to show you. I can show you this diagram. If I go back here, this diagram. So you can see that stress components such as tau 11, and say if I draw stress components here as well. So this would be tau 22, tau 21, and tau 23. So for example, stress components such as tau 11, tau 21, and eventually if we draw it somewhere here, here in this space, you will see there will be a tau component, tau 31. So these components of shear stresses act along a particular direction. Okay, so thus traction vector is used to evaluate these components of stresses that act along a particular direction, and thus, since they are acting along a particular direction, thus they can be quantified in terms of a force acting along that particular direction. That's why we used traction vector to correlate all the stress components along with the respective areas that would comprise the net force that acts along the particular direction, and thus devise the relationship between this traction vector and the stress tensor. Okay, so it will basically imply, if this is I, then it will basically imply that all the stress components that generate force along the ith direction can be included in this particular traction vector. Okay. Yeah. So this is what I was exactly talking about. From the conservation of angular momentum, we found out that these stress components, the stress tensor is symmetric. So tau ij is equal to tau ji. Okay. Then we stumble upon the concept of pressure, which is the normal force that acts inverse in the inverse direction of the fluid element, and we found out that in the case of when the when the fluid is static, this pressure varies as with height given by the hydrostatic law. Okay, so that is again one of the crucial component for understanding the pressure. So I will just skip to that portion. Yeah. Okay. tension. Yeah. So before that, I think we should discuss about these parts, viscosity and surface tension as well, because I think I am skipping it very fast. So I think we should catch them as well. Yeah. So along with pressure, the other flow properties are fluid properties in specifically are the viscosity uh, and surface tension. Okay, so these are fluid properties. Okay, and we found out that this viscosity are originated for liquids and gases from different sources. For example, in the case of liquids, this viscosity is because of intermolecular forces of attraction between the fluid molecules, and in gases, this is because of the molecular transfer to molecular momentum. So we saw that in the case of gases, if we increase the temperature, this this movement of these individual molecules will be more amplified, which will result in a higher viscosity of the gases. That's why as the temperature is increased, the viscosity of fluid will also of the gas in this case will also increase. But in the case of liquids, since these intermolecular forces attraction are will be affected, basically will be decreased because of the increase in temperature, as the fluid molecules will tend to move apart. Because that's why the as the temperatures increase, the viscosity of these liquid molecules or the liquid in general in the bulk will decrease. Okay. Then we found out that in the these fluids can be uh, dissociated into or classified into uh, two major categories considering in terms of viscosity. So uh, these these fluids can be classified as the Newtonian fluids and non-Newtonian fluids, where Newtonian fluids are a type of fluids where the shear stress in the fluid elements is directly proportional to the shear strain. Okay, and for non-Newtonian fluids, this behavior is not linear and would rather have a power law behavior. Okay, basically it will vary as, say, tau will vary as a power of vary as theta dot to the power n, where n can be any value. For example, in the case of blood, n is equal to 0.7. In different type of fluids, n may vary as, say, 2, 3, anything. Okay. So, and this was the graph used to describe these different kinds of fluids. For ideal fluid, of course, since there is no viscosity, so the shear stress is 0. So the shear strain is there is no shear strain generated. That's why the shear stress will also be 0. So Newtonian fluids, since they are directly proportional to each other, it will give a linear line, and other type of fluids will show different kind of behavior accordingly. Then we discuss the concept of surface tension, which is basically the additional force in the fluid molecules that they have the additional forces that these fluid molecules have in order to retain their shape, even if there is a discrepancy of forces in the fluid molecules at the surface of the liquid. Okay. For example, if this is the free surface and this is the liquid molecule, then because of the cohesion forces between this lower surface of this liquid molecule and the liquid in the bulk liquid, the attractive forces between these fluid molecules and the bulk liquid molecule will be higher than the attractive forces between the upper surface of the liquid molecule and the vapor above the free surface. But then also because of this imbalance of forces, the liquid molecule will try to get dissociated. Okay, it will try to break apart, but then also the liquid molecules tend to retain their shape, and this additional force, by the virtue of which they are able to retain their shape at the free surface, is known as surface tension. And this surface tension force per unit length is defined as the surface tension coefficient known as sigma. Okay. So in the case of there's and these are related to and this surface tension coefficient for this for different cases are given. For example, in the case of spherical droplets, the excess pressure inside the spherical droplet is given by 2 sigma by r, where r is the radius of this particular sphere, and in the case of spherical bubble, it will have two different liquid layers. That's why you need to take into account the contribution from these two layers separately. That's why you have delta P as 2 times 2 sigma by r, which is 4 sigma by r. Okay, and then there was the concept of capillary rise, which is basically the balance of the surface tension forces that tend to hold this liquid column, and the weight of this liquid column then tends to pull this liquid column down. So capillary rise usually occurs when a very thin capillary tube or very thin tube is placed inside a liquid container, and because of the surface the adhesive forces between the this surface of this particular tube and the liquid molecules tend to pull this liquid molecule up. Okay, and we do a balance between the surface tension forces and the weight of this liquid column to find the expression for the capillary rise, which we found that for an acute angle of contact we get delta P as 2 sigma cos theta by r, or the capillary rise as 2 sigma cos theta by rho g r. Similarly, we found out that in the case where the static contact angle is greater than 90 degree, where it's obtuse angle, then delta P is given by 2 sigma cos 180 minus theta rho g r. Okay, and this is usually found out in the case of fluids such as mercury. Okay, so rather than the liquid level going up in the capillary tube, the liquid level tends to go down. Okay, it tends to dip, and the meniscus, that is the shape of the free surface formed in the capillary tube, the meniscus is in the case of acute angle, this is a concave surface, but in the case of obtuse contact of angles, for example in the case of mercury, they tend to form a convex meniscus. Okay, yeah, then we discussed about the fluid statics part. Okay, then where we see the variation of pressure. So let me just reiterate again. So the entire subject of fluid mechanics can be divided into these three fundamental parts: uh, fluids, fluid statics, which we'll discuss at first in today's discussion. Then after that, we will look upon fluid kinematics. And then fluid dynamics. Okay, so because of this constraint of time, I don't think I will be able to reach up to fluid dynamics, but since we already discussed in the last few weeks, so I think this should be quite fresh to you. But the basic thing is that fluid statics, as the name suggests, would infer to the concepts of fluid mechanics where the fluid is at stationary state. And we look upon the entire dynamics of the fluid flow, where we consider the forces as well as the motion generated, because uh, uh, we look upon the forces that acts on the fluid when the fluid is at stationary state. In the case of fluid kinematics, as the name suggests, in this case the fluid is in motion, but rather than looking upon the forces that generate the flow, we are more interested in visualizing how the flow behaves given that the flow is in motion. So we do not look upon the origin of the forces that drive the flow. But the theory would seem incomplete if we do not look upon the forces that generate the motion of the fluid. That's why in the fluid dynamics we look upon the complete analysis of fluids in motion, where we look upon the motion as well as the forces that generate the motion of the fluids. Okay, so that was the last part that we will discuss if we get time today. Yeah. For the fluid statics part, we start with the basic governing equation given by the Euler's equation of motion again, because since the fluid is at static state, even if the fluid is very highly viscous, it won't generate any kind of shear forces because of the velocities becoming zero. As you saw that these shear stresses are basically a function of this velocity gradient. So if the velocity itself is zero, there is no velocity gradient. That's why no need of considering these viscous forces. Okay. So the basic governing equation of motion in the case of fluid statics can be derived from this Euler's equation of motion given by this equation. So once you do that, when you find out the governing equation of fluid motion along the x, y, and z direction, we find out that along the z directions, the pressure gradient is balanced by the body force, that because of the gravity, and we found out that this relation dp by dz is equal to rho g turns out to be one of the very important relation to important relation in fluid statics, which becomes the base of different kinds of flow measuring devices, such as flow measuring devices, pressure measuring devices such as manometer. In fact, we use the same concept in the case of ventometer as well, where we use the similar manometers or piezometers to measure the pressure gradients. Okay. So this dP by dz is a rho g is known as the hydrostatic law, is indeed one of the very important equations in fluid statics and in fluid mechanics in general. Okay. So given this equation, we found out that this pressure is not constant throughout the depth of the fluid, but is rather a function of the depth of the fluid, where this pressure increases as the depth of the fluid is increased. For example, if we're measuring, say, pressure at point C and at point B, then pressure at point B would be higher because pressure is a function of this depth. Okay, and we will see what implication it has while we measure the forces on these submerged bodies. Okay. So then we look upon the principle of manometry. This again is one of very important concepts. Let me zoom out a bit. Important concepts, and we can expect questions in the exams on manometers. So let me just go through this example once again. Okay, it's basically a flow occurring from A to B, and here now we can just try to uh, correlate all the concepts that we have discussed till now. So if you would have attended the lecture by Professor Chakrabarty or the problem solving sessions, you would have understood by now that, for example, in the case of flow through this pipe or duct, whatever it may be right now, so let us consider it's a flow through a pipe. For a flow to occur, we need a negative pressure gradient, right? That we found out as one of the fundamental conclusions from the exact solutions of Navier-Stokes equation. We found out that dP by dx, or any axial dz also, no problem. But for example, if I consider the coordinate systems as, oh, let me write z only, so let me not confuse you. So for example, I cannot use z because I've already used z here. So for example, this x and y, okay, then this dP by dx has to be negative for the flow to occur in this direction, okay, in the positive x direction. So by now you would have understood that since the flow is occurring as shown in this shown by this arrow, for the flow to occur from A to B, pressure at point B has to be lower than pressure at point A. Okay, so that's why, since the pressure at point B is lesser than pressure at point A, it will displace a lower volume of liquid in the manometers compared to point A. So just by looking into this diagram, you should understand that the pressure at point B is lesser than pressure at point A. Okay, that's one of the conclusions. Now secondly, what we do is that in order to find a relationship between the pressure, or basically the pressure difference between point A and point B, we use the principle of manometry. Okay, so in order to do that, is basically what we do is we consider a datum which would ideally be the lower level of liquid lower level liquid column in the manometer. For example, it is at point C, the liquid level is at lower position. So when consider the datum to be at point C, okay, then these different heights or distances of these different points are given. So that's something that you need to find out. So what we do is, we know that from hydrostatic law, pressure at the same depth would be equal. Okay, since point C and point D are at the same depth, then pressure at point C and point D has to be equal. So what we do is we equate the pressure at point C and point D, and any discrepancy in pressure is taken into account because of this difference of fluids. Okay, we'll see how. So PC is equal to PD, then PC, pressure at C, would basically be pressure at A plus the pressure because of this particular liquid column. That is, say if the density of the fluid, that is water in this case, is rho W, then the pressure because of this length of liquid column would be rho W G Z1. So that's what we have written here. And then pressure at point D would be PB plus rho W G Z2 plus rho Hg, that is a manometric fluid used in this particular case, rho Hg into delta H times G. Okay, so that's what we exactly done here. Then just take B in the left hand side and take this term in the right hand side. From that you can find out that PA, after doing some calculation, we find out that PA minus PB is equal to rho, sorry, G times delta H times rho Hg minus rho W. Okay, so this is very simple. So any kind of manometer question that you can get in the exam, I think it should not be that difficult. And moreover, it more like the much difficult questions will not be asked. Okay, so it will be very simple, but you need to know the very fundamental principle upon which these formulas are derived. Okay, then yeah, then we look upon the forces on plane surfaces. So that is basically, if we submerge a particular surface in a liquid vessel, then what are the forces that acts upon, what are the forces that act on those particular objects? Okay, so these kind of scenarios become quite relevant when we are, say, designing dams or these structures that are made on water bodies. So in order to do that, we take the help of this equation given by yp is equal to yc plus ic by ayc, where it's important because here yc is the center of gravity. It is the location of the center of gravity from the free surface. Okay, as as I can show here. So h bar basically would be yc, the distance of center of gravity of this particular shape from the free surface, and yp is the center of, is the center of pressure or distance of center of pressure from the free surface. And the interesting thing is that the distance of the center of pressure in the case of static fluid motion is always greater than the distance of center of gravity, and this is primarily because of the fact that, and this is taken into account by this additional term given by ic divided by ayc, where ic is the area moment of inertia of the particular shape with the respective axis, and a is the area of this particular shape, and yc is again the center of gravity of, this is the center of gravity of the particular shape. So this discrepancy between the center of pressure and the center of gravity primarily arises because of the fact that the pressure distribution is not uniform in the case of hydrostatic condition. So this pressure, because of it, increases with the depth, as it is shown is as it is shown in this pressure distribution. So if you are going to take the, if you are going to find the center of gravity because of this pressure distribution, you find, I will not say center of gravity, but the center of balance, or I don't know what term to use. Like for example, if you are just trying to find, because of this type of loading, if you are going to find out what should be the center of gravity because of this type of loading, then you will find out that this will not be at the center, but rather it will tend to be tilted towards the lower half, just in order to take into account the higher pressure forces at the lower end of the surface of this particular shape. Okay, that's why this center of pressure is always at a greater depth than the center of gravity of the body in the case of uh, uh, fluid statics. Okay, then we solve different examples, and just for the sake of your exams, what you can do is you can look into these examples that I have taken in the class, also by examples by other TA as well. So it is a good exercise. So the crucial thing to remember is that in these kind of questions, remembering the formula for the center, this moment of inertia is quite helpful, as well as the center of gravity, because it will not be the case that all the time you will get the shape to be a simple rectangle or cube, so, or rectangle or square. Rather you can get something like a semicircle or a triangle as well. So according to that, you need to remember the formula for the area moment of inertia and the center of gravity of that particular shape. So that might come quite handy. Okay. Yeah, and then there was the concept of stability of submerged bodies and floating bodies. So we found out in the case of submerged bodies, the stability criteria was determined by the position of the center of buoyancy and the center of gravity. So if the center of buoyancy was above then the center of gravity, then the body was at stable equilibrium. By stable equilibrium, but I mean that if you are giving a certain tilt or displacement to this particular body, because of the location of the center of buoyancy and the center of gravity, it will tend to generate uh, it will tend to generate a restoring moment that will tend to revert back the shape of the orientation of the body to its initial position. Okay, but in the case of unstable equilibrium, if you are giving a certain particular displacing moment, then because of the location of the center of gravity and the center of buoyancy, it will tend to displace the body even further and just and thus result in a unstable scenario or unstable equilibrium. So if for the case of submerged bodies, okay, fully submerged bodies, if the center of gravity is above the center of buoyancy, then the body is at unstable equilibrium, and if B is at equal to and B and C coincide, then it is at neutral equilibrium. So whatever the displacement you give, the body will tend to remain at that particular alignment. But in the case of floating bodies, which is a topic of more interest from the perspective of fluid mechanics, the stability of these floating bodies are determined by the location of the center of gravity and the metacenter. Okay, so we found out that the location of center of buoyancy is not fixed in the case of floating bodies because of the area that because of area of the body that is under the fluid is changing when the orientation of body changes. So since the area of the body or orientation of the area submerged in the body changes, then the location of center of buoyancy also changes, and it is the line drawn from the center of buoyancy to the axis of the body where these two lines meet. This point is known as the metacenter. Okay, and we found out that stability criteria is that if the metacenter of the body is above the center of gravity of the body, then we get a stable equilibrium, and if metacenter of the body is lower than the center of gravity, then the body is unstable, and if this metacenter coincides with G, then it is a neutral equilibrium. And there was one more interesting scenario discussed by Professor Chakrabarty. So he pointed out that if M is above G is the stability criteria, then it is quite intuitively understood that if we make the body like quite long, like if we tend to push the what to say tend to generate like a taller shaped body, then the metacenter would obviously be at a higher location that would create a much more stable scenario. But he also pointed out that if this metacentric distance, that is from distance from the center of gravity to the metacenter, is very large, then it again creates different kind of issues. That was basically he took the example of a ship, that for example if the metacentric height is too much, then any kind of displacement to the ship would create discomfort to the passengers traveling in the ship. So it's usually a compromise between the comfort of the passengers as well as stability of the vessel, the ship in this case, that determines the metacentric height. Okay, so we cannot just continuously increase the length of the body in order to create a more stable scenario. Okay, so engineering deals with this kind of issues. Then we look into the formula for finding the metacentric height, where IYY here denotes the moment of inertia of this particular shape, and V denotes the volume of the submerged part of the body. Okay. Yeah. Then we look into the concept of fluid under rigid body motion, where the governing equation for this kind of scenario was found out from the fact that pressure at the free surface, the change in the pressure at the free surface is equal to 0. Then from that, using the concepts of complete differential and the Euler's equation of motion, we found out that the slope of this particular free surface can be found out to be tan theta is equal to ax by g. Okay, this is the slope of the free surface, and if this, if I go back here, if this height of the slanted surface is becoming higher, greater than the height of the vessel, then the liquid will tend to spill out of the container. So, and uh, this height of the liquid in the height of this slanted surface in the liquid container was determined by the acceleration of the acceleration of this vessel. So there might be some questions where they might ask, what is the value of this acceleration that would uh, that the body can reach before the liquid tries to liquid starts to spill out from the container. Okay. Yeah. So then, yeah, so then we come into the start with the start our discussions with fluid kinematics, and we then again reiterate the Eulerian and the Lagrangian approach. Okay, so in that we discussed about different kinds of flows. That was steady flow and unsteady flow, then uniform and non-uniform flow, and scenarios where the flow can be uh, steady and non-uniform, and scenarios where flow can be uniform and unsteady. Okay, so there was a very good example taken by Professor Chakrabarty, so I will skip that. Then we come into the main portion of fluid kinematics, this is fluid visualization. So we found out that for fluid visualization there are mainly three, uh, I would say, characteristics that we use to define to visualize the flows, and these characteristics are again popularly known as different lines, because these visualization are usually can be obtained as in the form of line segments. Then I would not say line segment, or I would say, I should ideally say it in the form of curves, and these characteristics are known as streamlines, streak lines, and path lines. Okay, so let me again, just for your recapitulation, go through the formal definitions of the streamlines, streak lines, and path lines. For streamlines, the important thing is that streamlines can never be visualized in real life flows. Okay, streamlines are always imaginary. So streamlines are imaginary lines in the flow field such that the tangent to these lines at any point represent the velocity of the fluid particle at a particular instant of time. And we have the equation of streamline are found is given by this equation, this relation. Then streak line is the locus. Streak line is the locus of the fluid particles which at a particular at some prior instant of time have passed through a common point. And in general, uh, when we try to visualize the flow using, say, tracer particles or fluid dyes, it is the streak lines that we are usually visualizing. Okay, not even the path lines, but the streak lines. For example, if we are injecting the flow at the dye at this particular location, okay, say x0 y0, then the first dye molecule that was injected at, say, point t1 would traverse a distance, like would be injected at this point, and then, say, traverse a distance and reach at this point. The second fluid dye molecule that was injected at this point might have again traverse a certain distance and reached here, but of course it will not reach further than T1 if the flow is not that chaotic. Okay, if it is considerably laminar, then it will follow this pattern. Then again the third particle reach a distance this, and the fourth particle reach a distance like this. So the line that connects the locus of this particular fluid the particular fluid particles, or in this case these dye particles, is that have passed through a common point at a prior instant of time is known as the streak line. Okay, and finally streamline is the basic description of the Lagrangian point of view. Basically, we find out the trajectory of a particular fluid molecule for the entirety of your for the entirety of your simulation or your experiment. Okay, for example, if the particle was injected at, say, x0 t0 at time t0, then we tend to, after t1 the particle might have reached at a distance, say, 0.1, and after, say, time n, then the particle might have reached a location x and y at time tn. So this track that was followed by this particle, say, from time tn, from t0 to tn, is known as the path line. So one very interesting conclusion that we have in this part is that for steady flows, streamlines, streak lines, and path lines are identical to each other. So, for example, if you are able to generate steady flows, or uh, essentially you are able to essentially generate steady flow in your lab environment, then if you put a die to visualize the streak lines, they will essentially be similar to the streamlines and the path lines, because in the case of steady flows, these three are identical to each other. Okay, then after that we look into the functional form of acceleration in the case of Eulerian approach. So we found out that in the case of Eulerian approach, the acceleration of the fluid molecules will not only be a function of time but a function of space as well. So we discussed very thoroughly how the variation of the property through space can generate acceleration. Okay, so we took a very good example, that was the case of a flow through a nozzle, where the flow at the inlet and the outlet like is essentially steady flow, but because of this convergence of this particular nozzle, uh, because of this converging section, the flow is getting accelerated. Okay, even if the flow is not, the incoming flow is not varying with time, but because of this change in the area and because of mass conservation, this flow is getting accelerated, and this is the type of acceleration that is taken into account by this advective term of advective acceleration terms. Okay, or the convective acceleration terms. Okay, so yeah. Then we look into the different form of fluid deformation, that is linear deformation and angular deformation. So I'll try to move a bit faster. Okay, and from while we were discussing about this fluid deformation, we were able to find the form of the mass conservation given by this equation. This is dou rho by dou t plus nebula dot rho b is equal to 0, and in say Cartesian coordinate, this is given by this equation. This equation also is also popularly known as the continuity equation. Then I will try to skip a bit for faster. Yeah, we looked into some examples. We solved these equations, this mass conservation equation, to find out the, say, given your velocity field is given, then you can use the mass conservation equation to find the other velocity component. Okay, because of the relationship between these two, this is, if say v component is given, then dou u by dou x is equal to plus dou v by dou y equal to 0, then you can find the respective u component. Okay. Then we took ample amount of time to solve different kind of problems for this mass conservation equation. Then we look into the angular deformation of fluid element, that is basically that generates these shear stresses. So we looked into the functional form of this of the strain rate tensor in the Cartesian coordinate system. For example, E dot x epsilon dot xy will be given by dou u by dou x plus dou u by dou y. And similarly, the other components can be found out. Okay, and in general, in tensor notation or index notation, this strain rate tensor is given by epsilon ij is equal to dou ui by dou xj plus dou uj by dou xi. Okay, this was the form of the strain rate tensor. Then Newton's law of viscosity can be written in the index notation as this: tau ij, this is the shear stress, is equal to 2 mu epsilon ij. Okay, epsilon ij is half of dou ui by dou xj plus dou uj by dou xi. Okay. Then look upon similar to this, we can also find out the angular velocity in the index notation, which is given by half of dou ui by dou xj plus dou uj by dou xi. Okay, and was similar to this strain rate tensor, and angular velocity will also generate a second order tensor, which we will have respective 9 components. Okay. Yeah, and then this was one of the important concepts, that is the stream function. Okay, so till now we found out that for, say, when we're dealing with 2D flows, then we'll have to deal with two different variables, that is u and v, to find out to basically to get an understanding of the flow field. Okay, but scientists found out that in the case of 2D incompressible flows, rather than dealing with two separate variables such as u and v, what we can do is we can define another variable, for example psi xy, which is able to relate both u and v by this relation as shown here, that is u is dou psi by dou y and v is minus dou psi by dou x, and this substitution inherently satisfies this continuity equation. Okay, and if you are able to find the functional form of psi with the respective choice of boundary conditions, then rather than having to deal with u and v separately, you can just find the functional form of psi and then just solve for psi and easily find out the value of u and v. Okay, and similarly, like you know that after mass conservation we look into the momentum conservation. So for example, if you are trying to find the pressure field using the velocity field, so what you do is, if the flow field is 2D incompressible, then just write these equations in the form of stream functions, find the functional form of stream functions, and then solve for the velocity from the stream function, and then just substitute these values in the momentum equation to find out the form of pressure. Okay, so that's a very standard procedure that is being used to solve or to get analytical solutions for 2D incompressible flow fields using stream functions. That's why it is much more simpler to solve 2D incompressible flow fields even for different complex scenarios, because psi could be found out. But the main issue turns out, the main difficulty arises when we are trying to solve for 3D flows, because for 3D flows psi cannot be defined. Then again, rather than having to deal with a single function, we have to deal with 3 velocity components and the pressure field. That's why it's the Navier-Stokes equation in 3D is still unsolvable. Okay, at least analytically still unsolvable. Then similar to stream function, we look upon another function that is usually used to characterize these flow fields, that is the velocity potential. So if the flow field is irrotational, then the velocity potential can be defined as v is equal to the divergence of the gradient of the function phi, where this phi is the velocity potential. Okay, so velocity components and the velocity potential are related by this relation, that is u is equal to dou phi by dou x is equal to v is equal to dou phi by dou y, and w is dou phi by dou z. So you will see that velocity potential, the only criteria required for this is irrotational flow. So incompressible and 2D behavior is not required for the validity of velocity potential, and it can be defined for any kind of flows given that it's irrotational. But consider a scenario that where the flow is 2D incompressible as well as irrotational. In that kind of scenario, we can find the relationship between phi and psi, where we found out that these phi and psi turn out to be very interesting mathematical functions, where the lines of constant psi, that is the stream lines, and the lines of constant phi, that is velocity potentials, turn out to be perpendicular to each other, except at the stagnation point, that is where u and v are equal to 0. So it is again one of the very key conclusions that we can obtain from while studying these streamlines and studying the stream functions and the velocity potential functions. So one more thing was that for 2D incompressible and irrotational flows, okay, I have written it in red. For a 2D incompressible and irrotational flows, both psi and phi satisfy the Laplacian equation, that is nebula square phi is equal to 0 and nebula square psi equal to 0. So you will think that then what's special about these kind of scenarios? So the thing is that the solution for the Laplacian equations are well versed and well documented in the literature, so it's quite easy to find out the functional form of phi and psi, given that flow field is 2D incompressible and irrotational. Okay, and these kind of functions which satisfy the Laplacian equation are known as harmonic functions. Okay, so for 2D incompressible and irrotational flows, phi and psi are harmonic functions. Okay, so the type of questions that you can expect from these kind of scenarios is that you can especially expect questions where you will be given the velocity field. You need to find out the respective form of the stream function. Okay, so that's what you need to do. That's what that is the type of question that you can expect. Okay, let us see whether, okay, we didn't solve this kind of problems, but these are the type of questions that you can expect. Okay, Then we look upon the dynamics of in-viscid flows. Okay, so I think I will only be able to cover this part. So I think rest are quite fresh in your head. So this part, revision of this part, I think would be quite helpful enough. Yeah. So dynamics of in-viscid flow. Okay. So the first question that can come to anyone's mind is that why study in-viscid flows? Why be interested on in-viscid flows when we know that there is no fluid in the entire universe that has zero viscosity? So the thing is that uh, right by now you might have known you might have known by the concept of boundary layer that this boundary layer region encompasses all the viscous effects in a very thin layer very close to the surface. Okay, and the rest of the region in the flow field, essentially beyond this boundary layer, can be considered to be inviscid. Not that the viscosity of the fluid is zero at that region, but the velocity gradients, because of the presence of this wall, is not that significant in those kind of regions. That's why the shear stresses cannot be manifested at those regions, and that's why these regions, apart from the near wall regions, can be essentially modeled using this in-viscid flow assumption, and thus can be solved using the Euler's equation of motion. So Euler's equation of motion is basically the governing equation for in-viscid flows. Okay, right. Like the moment we remove this in-viscid assumption, we need to take the help of the Cauchy momentum equation or the Navier equation that we saw for solving free flow problems. Okay, so since now we are only discussing about in-viscid flows, then we can give our attention to the Euler's equation of motion. This is the basic form of the Euler's equation of motion that takes into account the forces that generate the flow. So till now we have not discussed what are the forces that generate the flow. We only discussed in the free statics where we found out that the only body force that was there, that was the gravitational force that generated pressure gradients along the z direction. But since now there can be motion in the x, y and z direction as well, so that will tend to create these pressure gradients in the other coordinate directions as well. Okay, and since the fluid is in motion, so even if the body force is absent, say in the x and y coordinates for example, the pressure gradients may arise because of the fluid motion. Okay, so we saw that these forces that act on this fluid fluid molecules or fluid mechanical system can be basically dissociated into these body forces and pressure forces, where, or I would say in general, surface forces, where the surface forces will comprise of the shear stresses and the pressure forces. Okay, so yeah, then considering some particular types of flows, we came upon the definition or the form of the Bernoulli's equation. So from that we found out that given the flow is inviscid and it satisfies the assumption that density is constant and the flow is steady, then we found out that this Bernoulli's equation, given by this equation, let me go back, given by this equation, that's P plus half rho v square plus gz, can be applied to any points, to any 2 points along the same streamline. Okay, to find out the variation of pressure, velocity and this the potential energy. But if the flow is irrotational as well, then this Bernoulli equation can be applied at any 2 points in the flow field. Okay, the restriction of these 2 points being on a streamline is removed when the flow is irrotational. Okay, yeah, so it is very nicely written here. You can take a screenshot or just look into it. So if this is the Bernoulli's equation, then the primary assumptions are that the flow is inviscid, flow is steady and the density is constant. Okay, that is the special case of incompressible flow. So there was again a very thorough discussion of what it is about, and this equation is valid for any 2 points along a streamline. Okay, but if the flow is irrotational, along with these three assumptions, if the flow is irrotational as well, then this equation can be applied for any 2 points in the flow field. Okay, that was the constraint or the assumption that is required for the validity of the Bernoulli's equation. So for in exam or in any kind of question where you feel that you can apply Bernoulli's equation to find out the variation of pressure or velocity, then I would suggest that even if it seems that it is difficult to, like, even it seems obvious that you can apply Bernoulli's equation, I would suggest that you write all these assumptions thoroughly. Or if, for example, if the exam is objective type, your MT exam will be objective type, right? then then also you just check whether these assumptions are satisfied or not. And if they are satisfied, then only go on to apply the Bernoulli's equation. Otherwise you need to, if the flow is in viscid only, then you need to approach by using the Euler's equation of motion. Okay. Then we looked upon different problems. We did thorough discussion. The application of yes. Now I think I can conclude by from with this the different applications of this Bernoulli's equation. So one of the application was siphon, where we use this kind of tube to extract fluid out of a container, where we keep the exit of this particular tube at a lower level than the free surface of the liquid at the container. And because of the suction pressure generated because of the application of Bernoulli's equation, we are able to extract the fluid out of the siphon. Okay, and again the assumptions are that the fluid is essentially in viscid in this particular tube, but again you know that this is again not possible, because the surface of the pipe will in essence will try to generate these frictional forces, and that's why the magnitude of the pressure, suction pressure that we get in reality is much lesser than the theoretical value. Okay. The other application was the use other application was pitot tube, where we found out that this pitot tube can be used to find the velocity of the fluid at a particular point in the flow field. uh, okay, so again we apply Bernoulli's equation to find the value of this velocity of the flow field at say point 2, which can easily be found out by knowing the pressure at these two uh, tubes, that is pressure at this pitot tube and pressure at the static tube. Then from this relation you can easily find out the value of velocity at this point 2, okay, which is the velocity of the flow in that particular tube. The and the thing is that this pitot tube is specifically designed and used to find the velocity of the flow. Okay. The other two devices other device that I'm going to discuss is venturimeter. This venturimeter, even if the governing equations seem similar, and in one way or another you can maybe devise an expression for velocity, but in reality this venturimeter is not used to measure the velocity, but rather is used to find the volume flow rate through that particular pipe or duct. Okay, so again they again use this same Bernoulli's equation at 2 points in the venturimeter. Then then they try to find the relationship between these pressure heads using the pressure measured at this particular manometer. And once they do it, they are able to substitute it back in the Bernoulli's equation, then find an expression for Q. Okay, where you can see that you can easily find out the value of Q using this expression, because all these parameters, that is rho m, the density of the fluid in the manometer, is already known density of fluid that you are using, other than the say that you are using in the pipe. You know that that will be water or air. Then you know the deflection of the manometer. Then you know the area of the pipe and the area at the throat. So area at the throat and the area of the pipe and the area of the throat. Since all of these things are known, you can easily use this to find the value of the volume flow rate. Okay. And then again there was the use of a coefficient of discharge to make this measurement of this volume flow rate much more accurate than the much more accurate compared to the actual values of volume flow rate. So we use a correction coefficient known as the coefficient of discharge to correct the measurement of this volume flow rate from this venturimeter. Okay, so similar analogy or similar calculations are also used for calculating the volume flow rate through an orifice meter, but again the difference just being that rather than having these separate sections of converging and diverging section, they rather have a uniform pipe. So rather than having a throat, they try to generate the similar decrease in velocity, so increase in velocity and decrease of pressure, basically this pressure gradient at this point and this point, by using an orifice. So they will have a pipe here and they will generate a orifice at this section, and they will use the similar governing equations to find the volume flow rate. So again the key differences being that the manufacturing cost for the orifice is much lesser than the manufacturing cost of this venturi meter, and again but the advantage of venturi meter is that they give us more accurate results compared to the orifice meter. But given that if the accuracy is not that important, rather a very, it's just the bulk behavior of the fluids that you're the pressure difference that you're interested upon, then you can easily use orifice meter in your devices rather than a venturi meter to cut out the additional costs. Okay, so I think that's all. And okay, just lastly I just like to conclude with the RTT, where it is the origin of the fluid dynamics part, where we use a mathematical transformation given by this relation, that is dm by dt is equal to dou by dm by dt of system, and is the particular property for whose change we are trying to measure, is related to the control volume approach by this relation, that is dou by dou t of rho n dv, where n small n is the respective intensive property of that particular property capital N, that is n by m. So the volume integral of rho n dv plus the surface integral of rho n vr dot n cap dA, where I will just reiterate all the terms here. So this relation is just used to correlate the control system approach and the control volume approach. Okay, so it's basically a mathematical transformation here, and here n, capital N, would mean the change of property of the system, of the parameter that we are trying to measure. For example, if you are trying to measure change of mass, then n would be equal to m. Then n, small n, is capital N by m. So if capital N is m, then n would be small m by m, that is equal to 1. For example, then if n is equal to momentum, then small n would be mv by m, so it will be velocity. Okay, just substitute that here, and this is valid for vector as well as scalar properties. And this Vr here is the relative velocity of the control volume with respect to the relative velocity of the fluid with respect to the control volume. Okay, so it is very important to know this is the relative velocity of fluid with respect to the control volume, and n cap is the normal vector of the normal vector to the cross sectional area across which you are measuring this particular integral. Okay, so of course you will have a respective inlet and outlet if the flow has. So flow has inlet and outlet, then for the outlet this term will turn out to be positive, and for the inlet this will be negative, because Vr dot n cap will turn out to be negative because of the opposite signs of the area normal vector and the velocity. Okay, in incoming velocity. Yeah, so I think time is up, so I will limit my discussion to here, and the topics after this I think are quite fresh in your head, so I think that will not cause any difficulty. But I hope this recapitulation session helped you out a bit to recapitulate all the concepts that you would need to study for your exams. So I'll just say again, all the best and for your exams. Just one word of advice is that look into the assignment problems. Okay, you have all the video recordings with you, so you can just look into the assignment problems and the respective solutions that I have discussed, as well as other TA might have discussed. So just go through them once, all the assignment problems before your exams, and I think that would be very good enough. Okay, look into the concepts as well, but after looking into the concepts, just go through the assignment problems for your revision, and I think that would be more than enough for your exams. Okay, you will do very great. Okay, so with that, then thank you, and let's all the best for your exam. And let's
Sir, I am going to put this PPT in the file.
Yes, the thing is, I always update this PPT in the NPTEL to the NPTEL, but I don't know where they upload it. So you can just mail them. Okay, you can just mail them and say just give us the PPT shared by the TAs, so that it is helpful for us. Okay, so it includes everything, so I think that will be helpful for you, right?
Okay, sir.
Yeah. Okay, then all
Sir,
the best. Yeah.
one so one last question I want to ask.
Yeah.
Are the questions based on statement based, numerical based, or fill in the blanks, or the just as we have shown earlier in the assignment?
Yeah, see, the thing is, question may be theoretical, question may be numerical, question may be fill in the blanks. But the thing is, it doesn't matter. You need to, even if the question is numerical, you will have to solve it in your rough paper and then find a solution. So the questions will be quite similar to the ones that are asked in the assignment. That's for sure. So that's why I suggested you to look into the assignment problems after you look into the concepts that were discussed in the class. That will be quite helpful.
Any reference books?
Reference book, yeah, book by Professor S.K. Som, Professor Gautam Biswas, and Professor Chakrabarty. This Introduction to Fluid Mechanics and Fluid Machines. Are you aware of that book?
No, sir, I'm not aware.
You can just find the internet. You can write it down the name. That is Introduction to Fluid Mechanics and Fluid Machines by Professor S.K. Som, Professor Gautam Biswas, and Professor Suman Chakrabarty.
Sir, what introduction? You are asking introduction?
Introduction to Fluid Mechanics. Introduction to Fluid Mechanics.
Fluid mechanics. Yes, sir.
And fluid and fluid machines.
Fluid machines.
Yes, by Professor S.K. Som. S. K. Som. Som is the surname.
Yes, sir.
Gautam Biswas. Gautam Biswas. And Suman Chakrabarty. That is and Suman Chakrabarty. That is the tutor of this course.
Yes, sir.
Yes. You can refer that book. All the examples are given in that book, so it will be quite helpful. Yeah.
Okay. Thank you, sir.
Okay. All the best. Okay. Thank you for attending the course and all the best.
Thank you.
Yeah.